Cellular confinement systems, also known as geocells, are widely used in construction for erosion control, soil stabilization on flat ground and steep slopes, channel protection, and structural reinforcement for load support and earth retention. Typical cellular confinement systems are made with ultrasonically welded high-density polyethylene strips or other recycled and inferior materials, and expanded on-site to form a honeycomb-like structure and filled with sand, soil, rock, gravel or concrete. History of cellular confinement. Research and development of cellular confinement systems began with the U.S. Army Corps of Engineers in 1975 to devise a method for building tactical roads over soft ground. Engineers found that sand confinement systems performed better than conventional crushed stone sections, and they could provide an expedient construction technique for access roads over soft ground, without being adversely affected by wet weather conditions. The U.S. Army Corps of Engineers and Presto Products worked together in Vicksburg, Mississippi, and experimented with a number of confining systems, from plastic pipe mats to slotted aluminum sheets to prefabricated polymeric systems called sand grids and then cellular confinement systems. Presto developed a number of key improvements and patented perforations, texture, use of tendons, and polymetric connections. Today, cellular confinement systems are typically made from strips 50 to 200 mm wide, ultrasonically welded at intervals along the width. The CCS is folded and shipped to the job site in a collapsed configuration. Research. Early research found that cellular confinement reinforced gravel bases are equivalent to about twice the thickness of unreinforced gravel bases, and that geocells performed better than single-sheet reinforcement schemes and were more effective in reducing lateral spreading of infill under loading than conventional reinforced bases. Extensive research has been conducted in recent years on CCS reinforcement for roadway applications at many leading research institutes around the world. To understand the mechanisms and influencing factors of confinement reinforcement, evaluate its effectiveness in improving roadway performance, and develop design methods for roadway applications. Han summarizes comprehensive research conducted at the University of Kansas, including static and cyclic plate loading tests, full-scale moving wheel tests, and numerical modeling on geocell reinforced base courses with different infill materials, and discusses the main research findings from these studies regarding permanent, elastic, and creep deformations, stiffness, bearing capacity, and stress distribution, and the development of design methods for geocell reinforced bases. These studies showed that base courses reinforced with geocells reduced the vertical stresses at the interface between subgrade and base course, reduced permanent deformations, increased elastic deformation, stiffness, and bearing capacity of base courses. Additional literature reviews can be found in Keefe al. and Martu al. How it works. A cellular confinement system, when infilled with compacted soil, creates a new composite entity that possesses enhanced mechanical and geotechnical properties. When the soil contained within a CCS is subjected to pressure, as in the case of a load support application, it causes lateral stresses on perimeter cell walls. The 3D zone of confinement reduces the lateral movement of soil particles, while vertical loading on the contained infill results in high lateral stress and resistance on the cell-soil interface. These increase the shear strength of the confined soil, which creates a stiff mattress or slab to distribute the load over a wider area, reduces punching of soft soil, increases shear resistance and bearing capacity, decreases deformation. Confinement from adjacent cells provides additional resistance against the loaded cell through passive resistance, while lateral expansion of the infill is restricted by high hoop strength. It has been determined that creep is not a significant factor due to the interdependency between cells and the importance of passive resistance of adjacent cells. Compaction is maintained by the confinement, resulting in long-term reinforcement. On-site, the geocell sections are fastened together by polymetric keys and placed directly on the subsoil surface or on a geotextile filter placed on the subgrade surface, sometimes propped open in an accordion-like fashion with an external stretcher assembly and sometimes held open by stakes. The sections expand to an area of several tens of meters and consist of hundreds of individual cells, depending on the section and cell size. They are then filled with various infill materials, such as soil, sand, aggregate or recycled materials, and then compacted using vibratory compactors. Surface layers may be of asphalt, concrete, or unbound gravel materials. Applications: roadway load support. Cellular confinement systems have been used to improve the performance of both paved and unpaved roads by reinforcing the soil in the subgrade base interface or within the base course. The effective load distribution of CCS creates a strong, stiff cellular mattress. This 3D mattress reduces vertical differential settlement into soft subgrades, improves shear strength, and enhances load-bearing capacity, while reducing the amount of aggregate material required to extend the service life of roads. As a composite system, cellular confinement strengthens the aggregate infill, thereby simultaneously enabling the use of poorly graded inferior material for infill as well as reducing the structural support layer thickness. Typical load support applications include reinforcement of base and subbase layers in flexible pavements, including asphalt pavements, unpaved access, service and haul roads, military roads, railway substructure and ballast confinement, working platforms in intermodal ports, airport runways and aprons, permeable pavements, pipeline road support, green parking facilities and emergency access areas. Steep soil slope and channel protection. The three-dimensional lateral confinement of CCS along with anchoring techniques ensures the long-term stability of slopes using vegetated topsoil, aggregate or concrete surfacing, enhanced drainage, frictional forces and cell-soil plant interaction of CCS prevents downslope movement and limits the impact of raindrops, channeling and hydraulic shear stresses. The perforations in the 3D cells allow the passage of water, nutrients and soil organisms. This encourages plant growth and root interlock, which further stabilizes the slope and soil mass, and facilitates landscape rehabilitation. Typical applications include construction, cut and fill slopes and stabilization, road and rail embankments, pipeline stabilization and storage facility berms, quarry and mine, site restoration, channel and coastline structures. They can be built as an underlying mass or as a facing. Earth retention. CCS provides steep vertical mechanically stabilized earth structures for steep faces, walls under irregular topography. Construction of CCS earth retention is simplified as each layer is structurally sound, thereby providing access for equipment and workers, while eliminating the need for concrete formwork and curing. Local soil can be used for infill when suitable and granular, while the outer faces enable a greener tan fascia of the horizontal terraces rows utilizing topsoil. Walls also can be used for lining channels and in cases of high flow, It is required that the outer cells contain concrete as cementitious slurry infill. CCS have been used to reinforce soft or uneven soil foundations for large area footings, for retaining wall strip footings, for load sharing of covers over pipelines and other geotechnical applications. Reservoirs and landfills. CCS provides membrane liner protection while creating stable soil, berms and slopes, for non-slip protection and durable impoundment of liquids and waste. Infill treatment depends on the contained materials: concrete for ponds and reservoirs, gravel for landfill drainage and leachades, vegetated infill for landscape rehabilitation. Concrete work is efficient and controlled as CCS functions as ready-made forms. CCS with concrete forms a flexible slab that accommodates minor, subgrade movement and prevents cracking. In medium and low flow velocities, CCS with geomembranes and gravel cover can be used to create impermeable channels, thereby eliminating the need for concrete. Sustainable construction. CCS is a green solution that makes civil infrastructure projects more sustainable in load support applications by reducing the amount and type of infill needed to reinforce soil. The usage of haul and earth-moving equipment is reduced. This in turn decreases fuel use, pollution and the carbon footprint, and at the same time minimizes on-site disruption from dust, erosion and runoff. When used for slope applications, perforated CCS provides excellent soil protection, water drainage and growth stratum for plants. The long-term design life of advanced CCS technology means that maintenance and the associated environmental costs are significantly reduced, as are long-term economic costs. Additional details. CCS strip widths, hence the on-site height, come in various sizes from 50 to 300 mm. CCS walls are usually made from textured or structured high-density polymer sheets so as to increase frictional resistance against the infill soil from displacement. CCS are made of HDPE, low-density polyethylene and non-woven heat-bonded geotextiles. CCS walls are typically perforated so as to allow for aggregate interlock through the cell wall and to allow for drainage from one cell to another. On steep slopes, CCS may have a tendon or cable extending through the central region up the slope and anchored to a dead man such as a pipe so as to resist down-gradient sliding of the system. It is important that an engineer-designed load transfer device such as an ATRA tendon clip be included in the design phase to assure success in the installation phase. The backfilling of CCS on long and wide slopes is quite labor-intensive. Construction equipment called pneumatic sand slingers or stone slingers have been used advantageously.